Modeling changing amplitude in midline. While sinusoidal functions can model a variety of behaviors, it is often necessary to combine sinusoidal functions with linear and exponential curves to model real applications and behaviors. We begin this section by looking at changes to the midline of a sinusoidal function. Recall that the midline describes the middle or average value of a sinusoidal function. Changing midlines. Example 1. A population of elk currently averages 2,000 elk, and that average has been growing by 4% each year. Due to seasonal fluctuation, the population oscillates from 50 below average in the winter up to 50 above average in the summer. Find a function that models the number of elk after T years starting in the winter. There are two components to the behavior of the elk population: the changing average and the oscillation. The average is an exponential growth starting at 2,000 and growing by 4% each year. Writing a formula for this, average equals initial multiplied by 1 plus r raised to the t equals 2,000 multiplied by 1 plus 0.04 raised to the t power. For the oscillation, since the population oscillates 50 above and below average, the amplitude will be 50. Since it takes 1 year for the population to cycle, the period is 1. We find the value of the horizontal stretch coefficient b equals original period divided by new period equals 2 pi divided by 1 equals 2 pi. The function starts in winter, so the shape of the function will be a negative cosine, since it starts at the lowest value. Putting it all together, the equation would be P of t equals negative 50 cosine of 2 pi t plus midline. Since the midline represents the average population, we substitute in the exponential function into the population equation to find our final equation. P of t equals negative 50 cosine of 2 pi t plus 2,000 multiplied by 1 plus 0.04 raised to the t power. This is an example of changing midline. In this case, an exponentially changing midline. Changing midline. A function of the form f of t equals a sine of bt plus g of t will oscillate above and below the average given by the function g of t. Changing midlines can be exponential, linear, or any type of function. Here are some examples. Linear midline. F of t equals a sine of bt plus mt plus b. Exponential midline, f of t equals a sine of bt plus ab raised to the t power. Quadratic midline, f of t equals a sine of bt plus at squared. Example 2. Find a function with linear midline of the form f of t equals a sine of pi divided by 2t plus mt plus b that will pass through the points given below. Since we are given the value of the horizontal compression coefficient, we can calculate the period of this function. New period equals original period divided by b equals 2 pi divided by 2 equals 4. Since the sine function is at the midline at the beginning of a cycle and halfway through a cycle, we would expect this function to be at midline at t equals 0 and t equals 2, since 2 is half the full period of 4. Based on this, we expect the points 0, 5, and 2, 9 to be points on the midline. We can clearly see that this is not a constant function, and so we use the 2 points to calculate a linear function. Midline equals mt plus b. From these 2 points, we can calculate a slope. M equals 9 minus 5 divided by 2 minus 0 equals 4 halves equals 2. Combining this with the initial value of 5, we have the midline. Midline equals 2t plus 5. The full function will have form f of t equals a sine of pi divided by 2t plus 2t plus 5. To find the amplitude, we can plug in a point we haven't already used, such as 1, 10. 10 equals a sine of pi halves multiplied by 1 plus 2 multiplied by 1 plus 5. 10 equals a plus 7, a equals 3. A function of the form given fitting the data would be f of t equals 3 sine of pi halves t plus 2t plus 5. Alternative approach. Notice we have taken an alternative approach by plugging points 0, 5, and 2, 9 into the original equation. Substituting 0, 5. 5 equals a sine of pi halves multiplied by 0 plus m multiplied by 0 plus b. 5 equals b. Substituting 2, 9. 9 equals a sine of pi halves multiplied by 2 plus m multiplied by 2 plus 5. 9 equals 2n plus 5. 4 equals 2m. m equals 2 as we found above. Now we can proceed to find a the same way we did before. Changing amplitude. There are also situations in which the amplitude of a sinusoidal function does not stay constant. Back in Chapter 6, we modeled the motion of a spring using a sinusoidal function but had to ignore friction in doing so. If there are friction in the system, we would expect the amplitude of the oscillation to decrease over time. In the equation, f of t equals a sine of bt plus k, a gives the amplitude of the oscillation. We can allow the amplitude to change by replacing this constant a with the function a of t. Changing amplitude. A function of the form f of t equals a of t sine of bt plus k will oscillate above and below the midline with an amplitude given by a of t. Here are some examples. Linear amplitude. F of t equals mt plus b sine of bt plus k. Exponential amplitude. F of t equals ab raised to the t power sine of bt plus k. Quadratic amplitude. F of t equals at squared sine of bt plus k. When thinking about a spring with amplitude decreasing over time, it is tempting to use the simplest tool for the job, a linear function. But if we attempt to model the amplitude with a decreasing linear function, such as a of t equals 10 minus t, we quickly see the problem when we graph the equation f of t equals 10 minus t sine of 4t. While the amplitude decreases at first as intended, the amplitude hits 0 at t equals 10. Then continues past the intercept, increasing in absolute value, which is not the expected behavior. This behavior and function may model the situation on a restricted domain, and we might try to chalk the rest of it up to model breakdown, but in fact, springs just don't behave like this. A better model, as you will learn later in physics and calculus, would show the amplitude decreasing by a fixed percentage each second, leading to an exponential decay model for the amplitude. Damped harmonic motion. Damped harmonic motion, exhibited by springs subject to friction, follows a model of the form f of t equals ab raised to the t power sine b of t plus k, or f of t equals ae raised to the rt power sine of bt plus k. Example 4. A spring with natural length of 20 feet is pulled back 6 feet and released. It oscillates once every 2 seconds. Its amplitude decreases by 20% each second. Find a function that models the position of the spring t seconds after being released. Since the spring will oscillate on either side of the natural length, the midline will be at 20 feet. The oscillation has a period of 2 seconds, and so the horizontal compression coefficient is b equals pi. Additionally, it begins at the furthest distance from the wall, indicating a cosine model. Meanwhile, the amplitude begins at 6 feet and decreases by 20% each second, giving an amplitude function of a of t equals 6 multiplied by 1 minus 0.20 raised to the t power. Combining this with the sinusoidal information gives a function for the position of the spring. F of t equals 6 multiplied by 0.80 raised to the t power cosine of pi t plus 20. Example 5. A spring with natural length of 30 centimeters is pulled out 10 centimeters and released. It oscillates 4 times per second. After 2 seconds, the amplitude has decreased to 5 centimeters. Find a function that models the position of the spring.